Hello, 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 hello. Hello, Alison.
There we go. Hello.
Hello.
Here we are. It's almost there. There we are. It's almost there, Jeaneth. How do I say Ganana?
So, good afternoon, everyone, or whatever other time zone that you are in. And so welcome all. And welcome to this November narrative twin talk on one of the hotly debated topics in research today, or rather two of the hotly debated topics in research today. One is the reproducibility of machine learning experiments, and each of those keywords are quite a buzz and debated as well. And so is the second talk, which is about the national research graph. I mean, how do they come together? Of course, they are both about shedding light or the giving transparency to the research. And in an era when we have proliferation of papers and as well as need for high level of impact and so on, these two actually are giving two different lenses or discussing a very important issue. But before we get into this, I welcome you all on behalf of machine learning for AU community of practice. And I also take take a moment to acknowledge the country. And we acknowledge and celebrate the first Australians on whose traditional lands we all meet, and we pay our respects to the elders past, present, and emerging. And in introducing the two talks, the first one is by Associate Professor Alison Specht from University of Queensland and her team, and the second one from Associate Professor Amir Aryani from Swinburne University. And but before we go any further, just one request. I'm going to post a sign-up sheet for those who are new to ML4AU. Please sign up here, assuming you are okay with that, and you can put your names and contact details, etc. So we would be able to add you to future meetings. And thank you. And with this, let me invite the speakers of the first talk. So that would be Ali Ben Abbes, Dr. Ali Ben Abbes, and of course, Associate Professor Alison Specht, and Dr. Jeaneth Machicao. And am I saying the names correct, Alison?
That's okay.
My apologies. I should have.
I shall introduce them. It took me ages to get Jeaneth's last name correct. So
certainly, Alison herself has a PhD from Queensland University and come from a long lineage of academics, I would say. And then she has teaching and research experience for more than 30 years, specializing in ecosystem processes, long-term observations, and collation and mapping of biodiversity data from diverse sources, and including extreme natural events, and as well as innovation and adoption of better conservation and land management. She has been a director of 2 synthesis centers and established International Synthesis Consortium, and was founding working group member of DataOne. And with that, Alison, I invite you to take over. We don't hear you. You need to unmute as well. Alison, do you mind unmuting yourself?
here we are.
Yes.
I will try again. I will try. Can you hear me now?
Yes, absolutely.
Inadvertently clicked the wrong button. Okay, so I will present a slideshow. Right. It has really been a delightful, a great opportunity to talk with all of you today. The three of us that have started this project, I suppose, under the auspices of Professor Pedro Correa, I've mentioned, are all part of this PARSEC project, which is I'll forward this to the next one. It is a project sponsored by the Belmont Forum as part of its collaborative research action on science-driven infrastructures innovation. So we are particularly interested in looking at bringing novel tools and innovative approaches into regular science projects. And I'm joined today by my colleagues. First, who will speak first, is Ali Ben Abbes. Ali is a postdoc with the PARSEC project who is based at the FRB CESAB, the Synthesis Center in France. And Ali specializes in AI and machine learning. Before joining PARSEC and the team in Montpellier in France, he was working as a postdoc researcher at the Cartel Laboratory at Sherbrooke University, Canada. And he received his PhD in 2016 from the University of Manouba, Tunisia, and in partnership with the University of Clermont-Ferrand in France. The next person you will hear from today will be Jeaneth Machicao, and she is the other PARSEC postdoc. We're very pleased to have both of these very excellent people working with us. She has a major in computing science from San Agustin University in Peru and an MSc and PhD in computational physics from Brazil. She's been the PARSEC postdoc for the past 3 years, as has Ali, providing expertise in machine learning and data analysis. And as well as that, she lectures. So, and she's led the publication of several of our articles, as has Ali. So we're in good company. And Professor Pedro Correa, who is in charge of the lab at the University of Sao Paulo, the Department of Computer Engineering, the Polytechnic School of the University of Sao Paulo. And Pedro is the direct line manager of and partner in PARSEC, the direct line manager of Jeaneth, and maybe soon to be of Ali, but as we move through the project. By the way, PARSEC is nearly 4 years old, interrupted by COVID, may I say, and there are 5 countries involved. So you can see here the logos of the funders, which all go through the Belmont Forum, and the United States, Japan, the French Research Organization, and the Research Organization of the Sao Paulo state. So, and we have collaborators from Australia, namely myself, and many of you will know Leslie Wyborn and Georgina Gurney, perhaps. And as you can see there. But again, before I start, we'll acknowledge our traditional owners and custodians, but I thank Nana for having done that already, which is excellent. Okay, now, again, before we start, we'd like to hasten to note that, of course, the second presentation was the one that Nana and some of you saw at the eResearch Australasia conference. As you can see, it's the bottom right, it's the most recent, but we had a very big workshop totally devoted to all of these tools, etc., that PARSEC has been talking about under the hosting of the data science team in Sao Paulo, Brazil. So we've been working through talking about the work that we've been doing in relation to an article, which we'll hear more about. But the question today is about what have we learned. So I won't talk too much about that, but if you like, they're both on Zenodo. and the first one embedded with quite a few other talks in which you may be interested. Okay, so the goal that we have at the moment is to improve reproducibility. And Ji Peng, a wonderful woman back in, oh no, it wasn't her, wrote, it was the 2011 Peng, who wrote about the gold standard in modern science is to achieve full replicability of scientific experiments, or when not possible, achieve reproducibility. And of course, this is, you know, like sharing data, the hand over the heart, we all believe in it. It doesn't mean we can do it easily. And in fact, it is a challenge. Besides the normal challenges of sharing code, and in the interests of time, I didn't include some of the fascinating graphs that Jeaneth put together for the previous talks, but which did engage a few people. But, you know, it's bad enough code sharing, difficult enough to code share, all sorts of things, difficulty in understanding incompatibility between claimed and presented results, particularly when people write up a paper. I'm not telling scientists much about this anyway, because the classic paper trail to work out that final ingredient or the final step in a sloppily written methods section of a paper is not unknown in all sorts of disciplines in science. And code is no different, of course. System settings are underspecified, and we've lost RB and library versioning, but of course that can be underspecified as well. So computational experiments are hard enough, but DL experiments are additionally problematic, as many of you will know. Huge volumes of data sets, misspecification of the model or training procedure. Ali was sitting in France with many people who were in a multidisciplinary team, and not all of them understood how long it takes to create the suitable software environment, the libraries, the version. Getting the suitable hardware or architecture is really very time consuming. And of course, good description of the experiments to avoid that paper trail. Not too bad if you can ring someone up and ask them, but pretty bad if you're actually relying upon the written word or the code itself. And it's largely difficult due to the complexity of the techniques used. And we've just popped up 3 rather important papers, that 2 of which will come back, we'll touch upon again in this talk. But we've just popped up 4 papers which rather well describe some of the complexity of the techniques and the considerations needed to achieve appropriate reproducibility in machine learning. Because a small variation in dataset optimization, hyperparameters, DL architectures and infrastructure, as I mentioned, Ali spent quite a while setting up the infrastructure for us, really can make a world of difference. In the case of datasets, missing datasets and changes to the data may lead to overfitting. So you may not be able to actually reproduce precisely what this group has supposedly got out of their data. Optimization depends on the network initializations and the neuron weights. And I shouldn't hasten through these, because I did have a comment at the research conference from someone who said, you went too fast through this, but this will be recorded and you'll be able to see it again and pause while we go through these points here. But I'm only doing the introduction, and Ali and Jeaneth will be the much more interesting people here. So I don't want to dwell too long on this slide. Hopefully, while I've been talking, you've been able to read. So for example, the architectures and the infrastructure that I've mentioned, you can have this overfitting and underfitting, depending on really quite a big suite of complex parameters. So you end up with, if any of those are misdescribed, it may affect finding the optimal model. And of course, different hardware will work with different numbers of processors. And that's going to be one of the interesting things as we move across our 5 countries. Do we, for efficiency's sake, run it all through the infrastructure and the architecture that Ali has set up in France, or can we make it more mobile, or is that going to create more problems? And we think now, of course, Ali and Jeaneth are very happy to. I'm very happy if they contradict me, and I'm pretty sure I don't think they have, but you never know. So as part of all of this, we wrote a paper, which we're pleased to have published in Earth and Space Science quite recently, and in which we propose some mitigation strategies, including a checklist that will improve reproducibility, both for the writer and for the reviewer and for the person who's wishing to reproduce a particular method. And that is, I commend you to read this paper. It's very carefully thought out. And this talk today will be, in a way, an entry point to the paper and to make it more cogent with your concerns. Now I shall hand over to Ali, and I hope he will be able to speak. Yeah, that will be interesting. Ali, you might have to be a co-host, and you can probably share what is your advice. I'm sorry, Nana, because I can move the slides on, but can Ali speak? I think he can.
Ali can speak.
Lovely.
And either you or him can share.
Yes. Lovely.
Okay. Thank you, Ghana, for this invitation. And thank you, Alison, and all the Parsec team to share together this presentation.
Welcome, Ali.
So, thank you. So, as Alison introduced the Parsec project, and the goal of to our presentation today is to present our experiment of reproducibility using deep learning or machine learning experiment. My talk is before Jeaneth. After me, she will present our experiment about the reproducibility in the context of the poverty estimation using satellite images and deep learning. So, my talk now is to you present the general context. To you present the general context of our project. So in Parsec, the context of our experiment is integrated in the context to use the combination between the satellite images and deep learning techniques to support the sustainable development goals. So here the idea is, for example, from satellite image, you can estimate the poverty or the wealth index. With the satellite image and deep learning, you can anticipate the climatic change. That's our goal, is to use massive data set for satellite image using other sources of information, such as socioeconomic indicator, climatic data, soil data, and make data fusion before the training and the training the deep learning in order to support the sustainable development goals. In our context, please next. In our context and our next, Alison. In our project, you have interested on poverty estimation. The idea is how to estimate from a satellite image, how to estimate the wealth of the poverty index. And since 2015, there are many works in the literature that have proposed to estimate the poverty or from the satellite image. The generic pipeline, the idea is to use socioeconomic as target data, thus using an index. And after that, you download the satellite image based on the geographic coordinates of the socioeconomic data. So the input is the target data is wealth index with satellite images. For the satellite here, you can use many sensors from daytime images like Landsat with 30-meter as a spatial resolution. You can use also the night light to make proxy between the electricity and the poverty, the wealth index. And you can combine also the two sensor to make to extract the future from the two sensor to estimate the poverty. And after that, before training, you make some processing or data preparation to make the split, because here there are specific context in images, because generally the village for that you have used in training is very close, and you make some techniques to make to split the data in order to avoid the overlap between the satellite image and to make them the same information in one to make the same information in the same split, training or testing or validation. And after that, you use the deep learning or deep learning techniques to make estimation. Please, next. In our there are paper that have published in 2010 20. The paper of Jeaneth is that good paper that you have that they have used 23 countries in Africa to estimate the wealth index using demographic and health data set, and they have a good R squared of 70%, and also the code is available with the GitHub link. For this, please next. And the aim on this paper is to use a combination between multispectral Landsat images and night light, and by deep learning. Here, the idea is to propose a deep learning model to combine the future from the two sensors, Landsat and night light, to make estimation. And as I say they have a good accuracy error, squared error of 70% at village level. And the originality of this work that they have used very large amount of data, 23 country in Africa, and I think 10,000 village that you have used in the training. For this, you have considered the Jeaneth model as reference paper in this in the topic of poverty estimation. For this, you have think to reproduce the experiment of Jeaneth first of all, and after replicate the Jeaneth by adding some other country and in the time, and add also 3 countries in the training, and after that you use the transfer, the apply the trained model in Africa to other country, as you have do the to apply the same model in Africa to Brazil and Australia and Japan. But next, please. But here just to present the pipeline generic the proposed methodology in Jeaneth. Here, the first step is to calculate the wealth index. The wealth index is an index calculated from the first compound of principal compound using response of question. That question for the economic question about the number of room occupied in house, if the house has electricity, the quality of water, the quality of toilet, that extracted directly from the DHS survey. You have the DHS survey at household level. After that, you calculate the wealth index at household household level, and after that, you calculate the first compound of the principal compound analysis, and make the average at village level. For each village, you have the geographic coordinate, the lat long, and based on this geographic coordinate, you have downloaded the Landsat and nightlight images. You make some pre-processing, some data preparation, as I say, to avoid the overlap between the satellite image, because the size of images is around 6 kilometers square, and in order to avoid the overlap between the satellite image, and also to assign the the close village in one split, in order to make a generalizable model that you can use for other village. And after that, you have they have used two CNN, pre-trained CNN ARSNet 18. For each sensor, you have used they have used the CNN to extract the future, and after that, apply ridge regression to combine the future from the two sensors to make an estimation. That's the generic, the proposed methodology in here. That that you have reproduced this pipeline using the same data set at the beginning. After that, you have added 3 countries in training, Madagascar, Comor, in the training, and also that just used the data from 2009 to 2016. And for our case, you have used the data from 96 to 2019. And you have, I think, around 40,000 village in our training. Next, please. And that you have, when you have reproduced this experiment of ye, that you have many problems and many challenges and for the reproducibility. Because first of all, the author of this paper have published 2 GitHub links, and for each link for GitHub is missing many steps. And also for the first step, that you have a problem in for example in missing information about parameter, about description, good style. There are many gaps in all steps. So that you have worked into GitHub link, and you have tried to add something, for example, and that you have make many time just to reproduce this experiment, because no description, good description, for example, just for the data, for example, as Alison, for the data, for example, just they have published the wealth index calculated. It's not the original data, for example. You didn't know how they have calculated this wealth index, for example, and how, if, for example, for our case, we will add the other country, it should be recalculate this wealth index. So any description, any information about how to calculate. And also, for example, there are many new exact parameter value setting. There are many parameters in this script they didn't have, for example, get make description for this parameter in order for our case to change or to make some so. And you have tried also to contact the author, but no response for this author. But finally, you have reproduced this and you have the same performance results. And after that, you have replicated and transfer to other the model for to other countries. For this experiment, just for me, I have worked on it, and also Jeaneth and the Professor Pedro and Brazil team worked on 2 other papers, and that's the aim. Please next. That's the aim of this presentation, is based on the 3 experiment, Yi and John. You have to do this paper and to present some mitigation strategy, how to improve the reproducibility from the author, from the reviewer, and how also to make some advices to put the GitHub, and how to describe the code, the scripts, and for the data set, for the deep learning parameters, how to define the hyperparameter, and also the main challenge in deep learning, as Alison said, is how to install the infrastructure and the environment, because now in deep learning is not no standardization for to use the infrastructure and the environment. And now I think Jeaneth, they have she present the used approach in this paper and the contribution of this paper. And thank you.
Thank you, Ali. Thank you very much indeed. I shall stop sharing for the moment because, and thank you everyone for your tolerance and your attention to this matter. We now have a recorded component by Jeaneth, who is indeed Jeaneth, and because it is 2 a.m., or at least it's probably about 2:30 now in Sao Paulo, so neither she nor Pedro are here. However, we seem to have an excellent share sound, an excellent presentation. So I shall hand over. I will, do stop me if you cannot hear. So this should
how
be
I wanted to
there
make
she
sure
is.
that
I'll get a preamble. Have you heard that? Has everyone heard that, by the way? I should have a look at the at
yes,
people's
Alison.
faces.
Yes, yes,
You heard?
Alison, we
Brilliant.
can hear you.
Thank you. I will go as quickly as possible. We cannot stop her. Okay, so this should be good.
Okay. Hello, so everybody, and thank you for inviting me, and Ali and Alison, you as well. I wanted to be with you, but unfortunately it's 2 a.m. in the morning here in Brazil. But anyhow, I wanted to make sure that we spread this work that we have been working with our team, and also to extend the inviting for Professor Pedro Correa, who is also my advisor in my postdoc here in University of São Paulo. So thank you also you for coming. So you have been introduced by Alison wonderfully, and also Ali, who has been showing the experiments and the troubles that he has been faced to reproduce deep learning experiments. So continuing with that idea, what I'm talking to you, it's about one solution that we can provide you for your community, the deep learning and artificial intelligence community, so that you can also be helpful of reproducibility. So this is for promoting also our paper, which is the mitigation strategies to improve reproducibility, especially in deep learning experiments. Okay, so in this paper, we have proposed two main branches. One is about a checklist of reproducibility, and the other one's a mitigation strategies, so that people that is trying to reproduce some experiments, how they can overcome this challenge, so that it would be more easy to them. So in this, sorry about that. It's actually here. So in this paper, what we have faced is, especially this picture, which means that in a typical paper where we have, for instance, our scientific problem that is being resolved, and we have a published paper. So the flow is when we have some problem, scientific problem, and we develop any deep learning experiments. And we as an author, we expected to publish this work that we have been working. On the other way, when we have already a paper that has been published, there are some readers, okay? We have the audience that is reading this paper, and maybe they are going to create or to see if there are gaps and to see to continue this cycle. So this is how usually how science works, right? So in this flow of scientific methodology, we have three audiences. So one is the writer, so it's the people that is reporting their experiments, and they want to achieve that their work is reproducible. We have also other audience, which is the people that is reading, or maybe a reviewer that wants to read any kind of papers and wants to check the validity of this work, if it's reproducible, or just to check the quality of these experiments. And we have other audience, who is also the people that is trying to reproduce or replicate some experiments. This is particularly for the case that people that is new for a new field, for instance, that is trying to look for any other kind of experiments and to make them reproducing these experiments, right? So why I'm here with you to talk about this, and what do you are expecting to have from these presentations that we are making? What we expected is that from these three kind of audience, you as a machine learning and artificial intelligence audience, you are in this community. Of course, maybe some of you are also in the reproducing or just reading any kind of papers, right? So as a writer, the purpose of this paper is that you will be reporting your experiments, and a measure to see if the quality of your experiments is good enough is by checking the quality of the reproducibility of your experiments. So what we want you is that you have a checklist that you could use it to see, to achieve it the most of this checklist to have the most of effective and productive experiment of deep learning, right? So this is you. We wanted to target you as an audience, as a writer of these experiments of whatever, okay? So if you're a writer, so you, we want you to show this checklist, okay? Of course, this is only the headers, but I'm going to show you which is this checklist about. But this is grouped in these categories. So each of these categories has sub-items, and each of them you are going to ask yourself if your code has achieved each of these steps. So from the top and below, we have first the description of the data set first. And the second, it's the FAIR principles. But by FAIR, we mean by the findability, accessibility, interoperability, and reusability. Another group is the description of the deep learning architecture, the hyperparameters, and all the setup for the hyperparameters. The next one is the infrastructure and implementation of these deep learning experiments. Then, of course, how do you, if the reported experimental results and the theoretical claims are good enough, reproducible. And finally, if the shared coding or the metadata and datasets and all of these sub-items that are inside this shared code. So how it look like this checklist? And here it is, of course. In the paper, we have also this same table, and this is the template. So later, maybe I can provide just a specific DOI just to download this template, and you can have it as a document or PDF and whatever, so that you can have it on hands and you can use it. So these are the 6 categories that I have mentioned, and each of them has these questions you to ask. So I'm going to show you how this looks like. And this is the table. Okay, and maybe a little bit. So for instance, just to show on one of them, this is, for instance, about the description of the data sets. Have you given the relevant statistics, such as the number of remote sensing images? In this case, we are asking about the data sets, right? Particularly, this checklist works also with remote sensing imagery, but it could also be extended to other kinds of data sets, street view imagery, or some other data sets from computer vision and whatever. So you ask yourself if you have given on your paper the relevant statistics of these data sets, or if the data set is open access, or if there are clear details of the training and validation of the data set, of course. If there are some explanations that need for preprocessing steps for these data sets, if there is a link downloadable version of the data set of the simulation environment, if there is new data collected, if there are complete enough description of the process of this data set, and so on. Okay, so this is this table, and it is the complete 6 criteria. And how we have made this is a compilation from other papers that has also been working with reproducibility and some guidelines and some recommendations, and we compile them into this one table for the deep learning experiments audience like you. Okay, so going back here. So what will we do with this checklist? Okay, so this table, as I mentioned, it compiles the efforts from other authors as well that has been proposed, for instance, as machine learning checklists, like the work from Pinot. Also the ones that showing the variabilities and difficulties from deep learning, specifically experiments like the paper from Renard. And also about the fairness of the deep learning experiments, showing which are the sub-principles that are most in common for deep learning algorithms and so on. And this is coming from Harley and also. So we compile them and organize them so for you to have this checklist, right? So how do we use it? We use it also by doing the hard work, which is by reproducing other people's work. So Ali has shown you the work from Jeaneth and the difficulties that he has faced to reproducing this particular paper. We have done this for the other ones, these 3 papers. For instance, the case from Jeaneth, that it's a paper for combining satellite imagery and machine learning to predict poverty. Okay, and also a work from Suel that is using a street view imagery, and also for it's a machine learning experiments for poverty and estimation of other socioeconomical indicators. And the work that is also from Jeaneth that is using satellite image for predicting socioeconomical indicators as well. So these 3 papers are on the same topics. They are for deep learning, deep learning papers that are trying to predict, estimate some socioeconomical indicators, and they are using a kind of imagery that is huge volume. For instance, street view imagery and satellite imagery, it's a huge volume of data to be trained. So we have faced all of the many issues with these three kind of papers. Particularly, we have seen as a workflow, how do they work? It's by, for instance, we have these 5 steps. So, for instance, if you have some remote sensing data or street view imagery data, aerial data, whatever. Aerial data, whatever data set you have it. And if you combine it with whatever other data that you can have, or this is the workflow from the data collection, right? After that, we usually do the pre-processing and cross-validation of this data, where we typically can pre-processing these, aggregating this data, and making the data splits for cross-validations and so on. In this box here, it's what we actually do the deep learning experiment. So we plan it here, whatever is the deep learning architecture design, the estimation of the hyperparameters, and the training optimization. So whatever it's done, it's on this step. And after that, the last step, which is the evaluation of this model. So this is a typical summarized workflow from deep learning. And everything of all of these points are also, are also, how do we? And all of these steps are also aggregated in the implementation and infrastructure here on the top. So all of these steps use these technologies for which implementations, how do you implement the programming language, the libraries, and also the infrastructure, the computational hardware, and set up for this configuration of experiments, right? So thinking of this workflow and these steps that are inside here, we have seen that from the papers that we have tried to reproduce it, we have seen some difficulties. So we're using our own checklist here, and we have made some evaluation, a desktop evaluation for each of these cases. So probably you are also doing this for your own paper, right? So for instance, just as an example, regarding the data sets, we ask ourselves, is the data set from this paper has, the paper has relevant statistics such as the number of imagery that we have? So probably in this paper, we have some difficulties with that. So we asked it ourselves and they say, okay, this was partially information that was on the paper. But from the other papers was okay. Okay, so we put it just as a yes, just to having this information, okay? There were some points that we have a no. And for instance, the paper from J, this has a many difficulties, especially for the pre-processing steps of the data set. So this was also a no. And this particular checklist wasn't also doing by ourselves, but also our students. So here in University of São Paulo, we have it undergraduate students and master students that they have also tried to reproduce these same papers. And we ask them to fill this checklist. If they feel when they are trying to reproduce the experiment, if they have filled the completed steps to reproduce any of these papers. So we make an average of this information, and this is what actually are the most issues, challenge of most paper of deep learning have. Another important point here, and I'm going to show you this, maybe it's not huge, but this is the table, right? So what we have shown is that the most difficult parts were here regarding the data set. Here also regarding the FAIR principles. So for instance, most of these papers have been facing problems with the metadata and the data. So if the data has a persistent identifier. This was one of the most difficulties because most of these papers don't have a DOI for the data set that they have used. But of course, maybe it's difficult because, for instance, the paper from Jean used Google Street View imagery, which is kind of difficulty to have a DOI from the which it's actually imageries that he has downloaded. So, for instance, we have problems to have the same data set that they provide, and also the data acquisition that they have made is maybe not the same as the reproducing is going to have. So that's a problem. This also has happened with the paper from Swell, with the Google Street View and the Google imagery, the Street View imagery. So for instance, the data set, it's also difficult to obtain the same imagery, maybe to internet issues, some bugs, and the data of acquisition, it can be changed. So this is a difficulty. Also, most of these FAIR principles were not achieved by the paper of Jeaneth. But okay, it's not his fault. Okay, but what we want you is to be knowledge of these problems so that you could make your own work more reproducible for others and for yourself. Okay, so which ones were the most problematic? This one as well, the description of the deep learning architecture. So this has in common all of the setup, the configuration, how were the hyperparameters, if there was a cross-validation strategy to mention how was the split was made, if you have make some explanations or assumptions and explaining them. And for instance, if the hyperparameters were chosen manually, or if they have using some algorithm to make their, for instance, grid search algorithm to choose them, and so on. The other one was this one, the reported experiment result. This one also was kind of difficulty. If the claim of the results were the same as the ones that are reported. And this is also something that we should be careful, because sometimes our codes of the deep learning experiments are not the same that are reported on the paper. This could happen to everybody, because we have some version that is not yet the final version that has been published, or when we have been in a reviewing processing. For instance, what happens if we have finished our experiments and we made a paper and we submit for publication. And during the publication, we have the reviewing. And during that reviewing, maybe some reviewer says, okay, we have to, what about if you made some other experiments? And then you go back to your code and make some other stuff, but then you forgot to update what is in the code and what is released, right? So this is also something that we should care. And okay, we have also about how to, if we have to share the code, so where it's going to be shared and which repository, and to make it accessible for the others to obtain, and also to get citation for and acknowledge from your work, right? So coming back here, so we have this checklist, so you can use it for your testing your own work, right? So that's the purpose of this. And to summarize, our experience by reproducing these kind of experiments, and we have learned some of these stuff. So as I mentioned you, which are the most difficulties in reproducing? So these are the 4 categories that going back in our workflow. So the quality of the data set is one of the most important stuff we need to be careful, to be consistent in presenting our works. Regarding the deep learning experiment, how is the setup, the configuration and hyperparameters and so on, the implementation and infrastructure, and regarding to taking care about some of these FAIR principles, right? So these are, as I mentioned, these are the most frequent issues that we have when we face it with deep learning. So when you have to check the quality of the data set, we recommend you as a writer and also for the audience that is reproducing someone else working, is to check the data set, if it is completed, if it is well described, and to validate if whatever it's on the description of the data set, right? If you are just reproducing other works, so maybe you don't have the full data set, but you can use a sample of this data set. So you can use just a sample to test and to go on with trying to reproducing some experiments. Also, check the parameters of the data sets or the code. So whatever you have to make for instance, if you have an imagery of Google Street View, which are the dates that you are going to acquire, and to have the data management describe it well with which are the parameters that you have used just to get the data collection, right? As well, to check the pre-processing step, if you have made some changes to the original raw data and what pre-processing step you have taken, it should be written somewhere so that it's reproducible, right? Also, to verify the data construction method, it's very similar to the previous one, just to check how is the data set constructed, or if you are constructing a new data, right? Also, to test different configurations of data splits. This is particularly when you are reproducing a problem. So you're trying to set up the data configuration, the data splits, for instance, for cross validations. So to check if how the data was split, and to write it reporting this configuration. Regarding the deep learning experiments, so the most important thing is to provide workflows. Workflows are the most usable thing that me as a reader can obtain, because by a workflow, I can understand how the code is going to be run. So when I have some GitHub code, I know where it's starting the code and where it's finished. So I know which steps to follow. This is very, very important. So please share your workflows. Okay. Another point is regarding the model architecture as a source code. So to providing how was the setup of the architecture and so on. And also for different setups of experiments. This is particularly for the people that is reproducing, so that they can test other setups if they don't have the complete manner to reproduce a problem. So maybe they can test some changes on the code so that they can follow in the reproducing. Regarding the implementation and infrastructure of the setup of the experiment, so maybe we have some internet flows, and this is happening usually. So what we can do is trying to check which were the problems, or also you as a deep learning community, you can mention this on your paper. You can mention that you have probably faced these problems, and mention also on the paper so that people know it. Oh, okay, maybe I'm going to face this problem as well, and what I can do if it happens. Then I can have this information. Maybe it's a negative information, but it's useful for others to know that there are these problems. For instance, in Google Street View imagery, sometimes when you have batches downloading the image, it crashed. So the paper, the original paper didn't mention about this, but maybe if I have faced this earlier, then I didn't lose any time by trying to make other efforts to download it the mastery, right? So mention it, right? If we have found bugs on the algorithm as well, you can mention this on your GitHub codes or whatever repository you are using. Also mention about the versioning of the paper, of the code, which were the setup, the correct setup, the libraries, if it was using GPUs, which one GPUs, or other facilities for others, for the audience that is reading, right? Also, another point is about the branches of the code. This was a particular case, and I think Ali has mentioned this, especially in the paper from Jeaneth, where the paper has the official link on a repository on GitHub, but the same author has their personal account with the code that this was most updated. So, and this also repository has other branches that one was working and the other one not. And as a trying to reproduce this was very, very difficult, and it took months to try it to figure out how was the latest version and which ones they actually the one that was working, right? So this is also a problem. Okay, and also about the programming language, just to mention what are the language, if it also, yeah, this one is also about, for instance, if we have implemented our code in R code, maybe we can just say, okay, look, there is other people that has been reproduced my work and it's in Python. So we can just sharing these other repositories that say, okay, we have here our code of the methods in our language, and we have also in Python. So we can have it in other language just to help other people to face these problems. And regarding the FAIR principles, this is one important point. Of course, these are not recommendations, but just to be careful, just points that as a deep learning deep learning experiment we can face it. So these FAIR principles, as I mentioned, it's about the findability, accessibility, interoperability, and reproducibility of data or metadata. And by data metadata, we are also mentioning about source code. Our source code is also a kind of data that, okay, doing our experiments in a repository or whatever. So this source code and metadata are data sets that whatever we have producing, it needs to be taken care that it follows the fairness of this data, right? So just to making care if these principles are well enough described, and for instance, if we have to accept some uncertainty. This is particularly a difficulty because FAIR principles are actually achievable for data. When we're talking about deep learning, it's kind of difficult. And this is also what is mentioned in the work from Hartson and Olson. They say that not all of the FAIR principles are achievable by a deep learning experiment. So some of these principles are the ones that we should carry in deep learning experiments. So just take a look of them and trying to achieve the most that you can to make your work more reproducible. So just as a taking home message, what we are trying to let you to spread the word is that why are you doing this checklist and why it's helpful for you as a deep learning experimental and scientist using this technology. So the idea is that you use your checklist for making more reproducible of your own work. When you are publishing your work, it's going to be more cited because it's more trustable work. And also because you are helping the community to increase the visibility of your work, okay, by making it more reproducible. And it's because it's also a way to test your own work, how much reproducible it is, right? So as you said, if your deep learning experiment is reproducible enough, if yourself can reproduce a deep learning experiment, for instance, for other people, on how can you save yourself for wasting time, like we did by reproducing works by months. So use this proposal in this paper to make your work more reproducible. Okay, so thank you. Hopefully we can sometime be together in real life. Okay, and thank you.
Thank you all. And yes, that's an interesting talk about reproducibility of the machine learning experiments. I have requested for any questions to be answered in chat. I had only one, and a couple of other responses following that from Alison and so on. Are there any questions? I know it's a lot to take on, and yes, a hybrid.
I had, well, it's a comment and a question. So the paper it's in a very, it's not really very specific, but the paper is quite general for all areas, but it's in a more specific journal like the Earth and Space Science, and it's been out not too long because it's saying that at the beginning of August of this year is when it was published, and I was curious about the reception, if there's been much feedback, in particular from the three papers that are, I don't know, like name and shamed or whatever, but like that, but also just from people reading it and how wide, if there's been people that have commented from outside of this area and that kind of a thing.
Ali, do you want to answer that perhaps? We have a member of PARSEC, Roman David, who is very keen to make sure we actually do communicate and get feedback for these papers, of which we've had a couple. To answer you, I'm not sure whether, Ali, you have contacted Ye or Suel or Jean. Jean et al. Were quite communicative. You could talk to them and they answered the emails. So I know that was considered a great help initially, because that was one of the first papers. But you heard Jeaneth say the other, well, certainly, didn't reply. But I think you might have talked, Ali. Have you talked to the authors of these papers? And I can't answer for Jeaneth. I haven't asked that excellent question. It's a very, very good question. As for reception at conferences, we've only had really two outings. One was much more in-house to the Brazilian group, and we had a lot of people there and a lot of students who were used and tested it and things like that, and eResearch Australia. So yeah, you've given us a response, or are about to, which is fantastic. So maybe, unless we've got a direct one to the authors, certainly attempts were made to talk to them at various times. So Ali, what do you think? Did you contact? Jeaneth was the one who was talking to Sewell.
For me, just I have contact Ye and all the team, but the response is not very very quickly. Just to get some information about some specific question. And also in the GitHub, I have put some questions to. That's I have to.
That's good. Thanks. I was just curious if it's especially about those three, because it's not always, I don't know what the positive word is. It doesn't always feel good to see no on that table next to your name.
That's right. That's right. Although the context of the papers is quite important. I was involved heavily with the Sewell analysis, Google Street View, and Sewell's paper was conducted in London, where there are a tremendous amount of images that could give you a lot of information at high density about some of these socioeconomic indicators. So with our paper, the context was very different. It was an urban, rural, semi-rural environment. So, Sewell might have said, yeah, well, if you used Rome or something, you might have got an excellent result, or at least an easier result. So that was interesting, but that wasn't about the method, which is what this paper is about. My apologies. Anyway, Ming-Fang,
we have one
question.
We have Ming-Fang going to ask a question. Hi, Ming-Fang.
Hi. Yeah, thanks for the excellent talks. So that's comprehensive checklist. I just wonder, the checklist, when to use it. For example, machine learning researchers, most of them probably use other people's data. And also if they run, with big volume data, they run on cloud service as such. So should we advise the researchers, say, if the data set you are going to use could not meet those fair requirement. For example, you couldn't give a DOI, you couldn't ensure the interoperability or as such, or you are running the service provider for your computing could not give you the description of this service, then you should not to use this data or environment. Because in the end, when you submit a paper, if you don't meet this requirement, then there is chance to reject your paper or your reputation is online. Yeah. So yeah, that's my thought or questions.
Ali, would you like to reply to that? To Ming-Fang's question?
For the data, for example, when I say about the survey, just not to share the original data set. I think for our case, there are some restriction to publish the demographic and health survey. But the problem, for example, how to calculate this index, the wealth index from this survey. That's the question. When you put the data, it should be, for example, make some description. Okay, I am agree with that. You, in some case, you can't share our data, but you make some advices how to use this data, how to download, how to calculate, how to make some processing for this data set. That's
Excellent. Thank you.
Thank you.
I myself have some questions, but I think in the interest of time, let's move on to the next talk, Professor Amir Aryani, who is not a stranger to neither ML4AU nor our organizations. And so Amir is going to talk about knowledge graph networks. And this also sheds a lot of light on both the transparency and probably reproducibility, but also in the idea of how these different knowledge that is created would be linked and possibly might actually help in realizing an impact. Thank you, Amir. And before I go on, thank you, the three amigos, Alison, Ali, and Jeaneth. And thank you so much. Hope you might stay and enjoy the second talk as well.
Thank you very much.
Yeah, with that, I welcome Amir.
Thank you.
Hello, everyone. Okay, so Gunana, how much time do I have? How the time works before I start?
So you have, we have scheduled till 6 o'clock.
6 o'clock. So I'll try to
I'm
make
sure
that.
your talk would be would keep people riveted, even if you went overboard.
Let me see. I'll try to meet that deadline.
Yeah.
Okay, so let me share my screen. It's in the technology. You should all be able to see my screen by now. If the audio or video doesn't work, please let me know. Otherwise, I'll continue.
I can see the
Okay, cool.
this one, but only half screen.
Half of the screen.
Yeah.
Do you see the full screen now or not yet?
I think it is full screen, but half the screen is not utilized.
Are you sure?
Yeah, now it's fine.
Okay, that was part of design. Okay, so the topic of this talk is about a project that called National Research Graph, or also known as a National PEAT Graph. I'll get to this in a moment. But this would be a bit of technical dive into what this project can provide for researchers, but also I will talk about the benefits of this for overall community. This is very much an extension to what I presented in e-research. So I've tried to actually don't repeat the material that we talked in the research conference. My apology if there is something here that might be explained further. So if there is something here that you missed, you haven't seen my previous talk, just kind of ping and I'll expand on that. So what happened? Sorry, a bit of technical problem. Okay, back to the playing ground. Before I start, let me just simplify to say what is it that we're going to talk about. At the core, we are going to talk about a Neo4j graph database. It is a graph database that contains Australian research output. It has about 10 million nodes. It has about 17 million relationships, and it is accessible to researchers for non-commercial research. So the whole talk is about the background of this, what it is, how it came about, or how we are doing this, because it's very much a work in progress, and how you can use it. But just the big picture view is this is the core function of our discussion today. So the project is a function of the collaboration between a number of different universities. And the idea is that we basically have a collaborative approach with multiple different partners bring data together. There is a big donation from the Research Graph Foundation as a core data seed that provides the main function of the graph. And the idea is that we have researchers from different universities collaborate together to continuously improve and evolve this graph. So it is a collaborative enterprise in that sense. Now, why we are doing this? The major kind of driver of this project is gaining insight into the Australian research impact. But that is more at the research administrations. When it gets to the AI community and ML community, there's a number of other opportunities. So this is a playground for playing so many graph algorithms and social network analysis. We can test different AI algorithms around the entity resolutions and name disambiguation. It is a very good platform for tracing the digital footprint of research. So that's for the researchers in bibliographic space. It is a gold mine in some sense to be able to find exactly what papers are actually connected to what researchers and what grants and what organizations and how those networks work. It's about discovery of research and industry collaboration opportunities. There are ways to do that out of graph like this. And also it enables the researchers to collaborate and explore their own collaboration network. So very brief about the Research Graph Foundation that kind of made this project happen. Research Graph Foundation I'm one of the founding members of this entity that came out of the Research Data Alliance way back in 2012, where we were working on connecting the data repositories together. So it had attraction and collaboration of a number of different international partners. These days, the main things that this group does is that work on the research projects that benefits or drives connection between scholarly works. For example, we do the knowledge mining from the COVID literature. We work around the concept of interoperability between the data repositories. There's a new API that's called Augment API that can be used to create graphs out of the repositories. There's a number of different projects individually that all benefits from these scholarly networks, and that is a focus of the foundation. But in the context of this project, basically this foundation provided the seed data for the national graph to happen. And then we are relying on the collaboration of our partners in Australia to basically host and maintain the graph database across the network. Now, when we talk about the research graph, we are talking about these things. So I think my back and forth doesn't work as I expected. Every time I click a wrong button. Okay, I'll do that. No full screen. So when we talk about the research graph, we are talking about 5 research objects: the researchers, research data, organizations, publications, and grants. And these are the core research objects in the graph. Now, when we talk about the publications, it's all form of different publications, or from the journal articles to grey literatures to patents. Even in our environment, some of the social media feeds also considered as form of publication. So it's not publication in a traditional sense. And also data, again, we talk about all kinds of data sets, from the actual large scale data sets that come from the high energy physics to even a small Excel file that been published in a repository. Organizations is universities and basically any form of entity who is involved in the research as a group. And then grants also implies projects. So these are basically grants and projects are on the same type of note. Now, I would talk a lot about the persistent identifiers in a way that these are kind of like a building block of a graph. Research graph, in a sense, has a lot of nodes that they don't have a persistent identifier. But in the context of this conversation, we would rely a lot on the persistent identifiers because that is what drives the national graph. So persistent identifiers, I'm assuming all of you probably have heard about those. We're talking about the ORCID, talking about the DOI, ISNI, Scopus ID, Funder ID, Wikidata, and so forth. These are the identifiers globally that identifies research objects in the global network of scholarly communications. So we are talking about, in the research graph environment, often about 3 different types of connections. And I found it's important to always clarify this because this often creates or kind of clarifying this can remove some ambiguity from the conversations of what the relations in the graph is. So we have a type A connections. That is where 2 metadata records linking each other on the persistent identifiers. That is where inside ORCID accounts, you see the link to a DOI. We have the type B connections when it's not about the metadata, it's about the data mining from the PDF content. So you have a text from a paper that from that we find all other links from it. So that's not come from the clear metadata records. And then type T scenario is where we use a natural language processing to find connection between items is almost like using different techniques for name disambiguation to say these two researchers are the same. And there are so many methods for it. And often there's a probabilistic value attached to these type of connections. Now, in the context of this talk, we are only talking about type A and B. That means we are not relying on the AI engine to create relationships. And the main reason for that is that it's that kind of relationship basically makes a completely overwhelmed graph with extra relationships that makes it computationally very difficult to use. That kind of method, we use it for specific use cases. So type A and type B is all about persistent identifiers, either directly from metadata or from the links derived from the context of text somewhere else. Now, as an example of type A is that there's an ORCID record that has a connection to a number of different DOIs. There's a type B where we find those DOIs in a paper, as like a data, the citation networks, or you can find a link to a grants or ORCID IDs inside publications. And there's another example of type B connections when we actually have a name of organizations and then we match them to a Wikidata node. Again, this is another connection happens to the Wikidata links. And then we have type T as an example of this. I kept it here just to provide a context. We have a project, for example, working on this for quite a while that connect papers to the Sustainable Development Goals. And it uses existing papers in the graph to build a neighborhood networks to find out other possible papers by authors that can be related to different Sustainable Development Goals from UN. So going back to the promise of type A and type B, when we talk about a PEAT graph, the global network of persistent identifiers, that is what Research Graph Engine on the on Azure Cloud ingests. As today, it has about 383 million nodes and it's about 800 million relationships. So it's a substantial graph. It includes all the papers that ever received a DOI, all the ORCID records, all the grants that you get from the Australian funders or European funders or NIH or NSF and so forth. All of those public records about the persistent identifiers. PubMed is part of it. Archive is another one. There are some social media records in it. So you can see some of those in this slide. But the side effect of this is, or the byproduct of the graph of this scale is that it's not consumable in a way that you basically run it on your notebook and then start operating queries on that. Its size implies that it requires a specific engineering for getting the optimum queries out of this. And also it requires a cluster of machines to run efficiently if you want to get your queries in a reasonable time frame. And that's where we get a data tsunami. So that is the point that we say, okay, so much data that really is hard to use. It's useful for specific cases. We have a Apache Airflow network that reads information for that purpose. However, for our project, we need something smaller. So we start building this, but we are focusing on Australian researchers and Australian organizations. So we have identified about 1,500 Australian organizations as a core of the graph, and that forms the national PEAT graph. And then everything that links to these organizations and the collaborators of these researchers who work for these organizations and what they have done and what the grants that they got. So it's basically a start from that core point and then goes out. So a graph like that as a seed point has only 10 million nodes and 17 million relationships, much smaller than the global PEAT graph, but still it's quite a sizable graph. 10 million node graph is not a small graph per se, but it's much more manageable. You can run it on a VM and you can operate with it. And I'll show you in a quick demo how you can actually access the interface of this graph very easily from your computer. Now, the characteristics of this, or the aim here is that it's focused on Australian research. It's supposed to be accessible to researchers, so you should be able to work with it with Jupyter Notebook, REST API, And the most important thing is that the Neo4j toolbox, and there's a lot of those, make it easy to understand and digest. The other thing is that the different typology of nodes in a complex graph make it very difficult to understand what is happening. A smaller graph by nature is easier to understand. There's a less diversity in included data sets and data type in it. From the different sources, not from the type of nodes, is more about what sources are included in the graph. And I'll mention the sources and types and all sorts of characteristics of nodes are what we call them labels in the graph that you can actually manage by those characteristics. Now, it's computationally viable to use as a database and make it possible to store on different university networks. So it is Neo4j, as I mentioned. I don't know how many of you have experience with Neo4j. I'm going to give you a brief demo, but it is one of the most usable graph databases that I've seen. It's extremely easy to pick up. We even have an easy time to train students to start using the graph database using the Neo4j technology. So it is approachable by most programmers, and the environment of that is reasonably user-friendly. Now, it uses a language that called Cypher. It very much looks like a SQL statement, but it's based on the graph. Like I have a very basic Cypher query that says there are two nodes N and M, and are connected by a relationship. And it says return everything for me and give it a limit. You always give a limit, because when you are dealing with a very big graphs, queries like this can return everything. And then that as a result will take a long time to come back. I believe these slides will be available. There's a link here. There's a very useful link that takes you to the Neo4j page for all different formats of queries that you can type and things that you can do. Is very handy, and it's still, after all of these years, I keep going back to this when I want to type complex queries. So before I fire up the actual Neo4j environment, as I mentioned, the graph, everything in the graph have labels. So we have two types of labels for every node. And the reason I'm showing this before getting to the graph is that this is kind of one of the core foundations of the research graph schema. Every node has one of those 5 types. It's either a researcher, a grant, a data set, or organization, or a publication. But also a node has a source. So that node metadata comes from different places. So the node metadata can come from university, can come from ORCID, can come from Crossref, DataCite. In the case of National Graph, we only included public metadata repositories, and in this case, persistent identifier providers. So the sources that you see here is things like ORCID, Crossref, DataCite, PubMed, the common main metadata providers. But for our other major clusters, you would have all different type of source labels that identify where the information come from. Here, for example, in this example, you see we have nodes from Scholex, we have nodes from Twitter, so they are still included in this national graph. So let's type some live Cypher queries. Before I do that, any question for me until here?
Yes, Amir, does that Cypher query return exact match, or is there some ranking involved?
No, Cypher query is like a SQL query. It gives you the exact match. So I'll start here with some very basic ones, clear my playground. So let's just type the basic Cypher query that I showed. So if you say -r, this is basically about the structure of the graph. There is no filtering here. So give me any two nodes that are connected by a relationship, return all of it, and please stop at 100, otherwise it's going to take a long time. So then this is going to talk to the server and return the result. So this is the result of the graph, if you like, things that are interconnected in that space. One of the things you will note is that I'm using the local host. It's not actually a local host. I'm using a port forwarding through the SSH to the server. So at the end, I'll explain how to connect the server. we usually give you the IP address. You can just connect with the IP address, but in my case, I usually use port forwarding. It's more secure. So that's a very basic Cypher query. But now we want to do things that are slightly more advanced. So if I say I want to give it some form of types, I want to get a researcher. Give a bit of a zoom so you can read it. It says I want to have a researcher is a label that's connected to a grant, and then run the query. So here I would have, if you remember the color coding of research graph, the yellow ones are the grants, and the green ones are the researchers. So here you can actually see all of our nodes are interconnected. There is no filtering here. Still, there is nothing specific except saying what are the types we want. I can go something more advanced by adding a name of the person. Sorry. In this case, I would say I want to get the ORCID of the researcher that actually connects to anything else. And I know the name of this person is Amir Aryani, and I just stop again at 20. So this would returns the researcher with the ORCID record and all the other orange one, all data sets, and all the yellow ones are the grants, kind of, and the publication. And we stop at 20. We could raise the link to 100, and then you get a bigger graph. Now we can do something with organization. So let's try this. Actually, maybe before that. Yeah, that's better. So this one is just, I'm asking from list of my nodes, give me a list of organizations that are from the type Wikidata, and then just list two properties of those, which is a key and a name. As it does, it gives me the list of the Wikidata nodes and the list of organization names. As you see, things like universities this is actually most of them are universities, but if you get a longer list, with the CSV files, you can be more generous and ask even up to 1,000 nodes, which usually works quickly. I hope. That might have been a bad idea. Yeah, let's estimate 100. Okay, this is much quicker. The other thing to remember, and this would I need to kind of come back to this later on, is that I'm just right now connecting to one of our nodes, and the number of people who are connecting to those nodes, every time someone runs a query, it consumes the resources from other people. So you would the performance gradually diminishes based on the number of people who are connected to the server. So as we are starting to get more people using this server and this node, we started to think, okay, we have started to create another node, which then our next node would be at NCI. So here you would see different colleges, different universities, and sometimes even local governments. Now, we are, when I was doing this, I thought, okay, let's look at find a specific Wikidata ID. And in this case, I am looking for the University of Sydney. So this is where you can actually learn another command, which is contains like a SQL statement. So it says from the Wikidata records, give me a record and a name contains Sydney. If I run that, it says, well, University of Sydney is this one. So I have it. And then I can run a query based on that. So I think I also typed that one before. That was my last query. Yeah. So in this case, I would say my organization links to another node. Oh, the other thing about Cypher is that you don't always have to type that relationship in the middle. This system is smart enough that you may escape the relationship. It understands it. We usually use that if we want to do something with that relationships. And the way that it is functional is that relationships have their own properties. So you can filter relationships based on their characteristics. For example, you may want to, in example, between organization and researchers, some researchers are student in organizations, some researchers are employees, and those are encoded in some of the research graph nodes and relationships, so you can actually filter by those properties. If you don't need it, you can just skip it and just have a very specific list of nodes linked to each other. So in this case, we have an organization linked to anything else, and then we know the wiki data for that, and so give me 100 node from that. So then we see the nodes related to the University of Sydney. So there is a lot of things that can be done in the graph database environment. You can basically crawl through different nodes. For example, if I look at the crossref nodes, you can see all different publications. You can click on those things, so it gives you the link to researchers. You click on the researcher nodes, give you more links, and this is what we call crawling in the graph. And it never stops. So you can just go on and on and on. Click on big university. I think it's going to give us a lot of nodes. What that node is. Oh no, that's it. Not. Yeah, if a node has more than, yeah, that's what I was going to say, is that bad idea to clicking on the organization nodes because it has so many things attached to it that this will happen. Take a long time for a result to come back. Okay, so this is how the Neo4j environment works. Obviously, it's useful to understand what is in the graph, but the main role or function of this would be using the Jupyter Notebook or your own programming environment, and then try to pull the information out of this using the coding, basically. Now, other thing I thought worth mentioning is that we also have the engine of creating visualization dashboard top of all of our graphs. And we have done also one for the national PIT graph, trying to understand what is included in that. So, right, and then full screen. So this is the structure of the graph, or we call it meta graph. So the national PIT graph as it is, it includes 631,000 ORCID profiles in it. It includes all of these publications. So the way that you read it is that there are 226,000 relationships between PubMed publications and ORCID researchers. And we're going to remember these are not all Australian ORCID researchers. These are also a majority of them are researchers who collaborate with Australians. So we had a count on this one. I think it's about 105,000 Australian researchers with ORCID profile. So the remaining of this are international researchers who are collaborating with Australian researchers. You can see the different organization nodes that come from different sources, or ISNI records, or Wikidata records, or GRID records. And then there are data comes from the grant information come from ARC, a lot of Crossref grants, and a lot of ORCID grants. And then we have the ORCID datasets, DataCite datasets, and Crossref datasets. Now, going to back to the other page, one thing we can see in a graph like this, refresh this one. Majority of the content of the graph or publication. So it's about 900,000 nodes, 9 million nodes here are publication, following by researcher, organization, grants, and datasets. And if we click on the, for example, Crossref, we can see Crossref mainly have publications, but it also has other things. It has datasets, it also have organizations, and it also have grants. So actually, yeah, very small amount around the grant, only 85 grants. Now, the other things about this national graph is that there are about 185,000 organizations across 234 countries that we have identified. Don't think there's anything particular to say here. It's kind of quite global coverage. But you can also see the list of different organizations in different states. And then the thing here is that the collaboration network of Australian researchers goes across universities such as Oxford, Columbia universities, and so forth. They're not surprising per se, but what I'm going to promising here is that the data that you had in the Neo4j includes all of this information. So you can actually write your own code to pull the data out of the graph. Now, going back to the kind of graph conversation. Now, how did we build it? The process of building the national PEAT graph. This is the last few slides before I open this for conversation. We use 3 degrees of separation from the actual PEAT graph. So we look for Australian researchers in a way that these are the researchers with profiles that have Australian affiliations in those. And then we look for their collaborators, the people who work with them on data sets, grants, and publications. And then we basically look for organizations attached to those. And then this is a collaboration graph. And then National PEAT graph is really the collaboration graph of Australian researchers. So we brought that together. So we built a pipeline that does this. But obviously, we first build a PEAT graph, and it's a small slice of it. There's a 3-layer infrastructure. So there's a PEAT graph, as I mentioned, that gets the data from different sources, and I'll explain in a moment more in detail how it works. But then we have an optimization layer, which does that filtering. Plus, it does some other things, and that's kind of, given the size of the graph is possible, we create a better entity resolution with Wikidata. We'll clean up some of the affiliations in the graph, and then we create a collaboration network related to the grant and publications with some extra data cleaning that we know based on the data information that we get from multiple sources. But then when we did all of these things, we pushed the information into our data access layer. And the promise of a data access layer here is that we have different networks in different universities, and researchers accessing these different copies of the same data set from their own university space. So as I said, in Victoria, Swinburne already has a node that we start to share with some researchers, and we are working with NCI to create our next cluster. And the idea is that we basically continue doing this. It will be another one for University of Canberra and so forth. And then we basically have the network of these Neo4j databases accessible to researchers. If you're really passionate about this and you want to have access quickly, I'll explain how you can do it. It's using the GitHub repository. You can do it today. We can find a spot for you in one of our access points, and you can start using the graph database, and then later on we will sort it out which database you would need to access. The PEAT graph layer that I mentioned, it is in a nutshell, it reads the information from all of these metadata repository sources. It pushes them into the pipeline, data pipeline, and uses the microservices in Apache Airflow to do all the linking and data cleaning. It stores a lot of information in MongoDB clusters. We have a whole cluster of MongoDB machines. And then the microservices, one of their job is that push the information to a Jenkins continuous integration server that from all the cleaned up data builds a Neo4j graph database. Now, this is at a very large scale, but we would need the same technology for the PEAT graph, for national PEAT graph. So the actual function of accessing this is we're managing this through the GitHub repository, and it is well, I have to click on this link. That would do. So this is a private repository, and I'll explain for one moment because we have some connections of our network. So at the moment, it is managed based on the concept of a trust, assuming there are still a limited number of people who are using this. So we have a file that holds the connection information for our servers. We already have one cluster with the IP address. which this IP address is changing all the time. That's why you need to have access to this machine. We often maintain the VM or swap the VM so that IP addresses are not quite fixed. We use a Slack for the main line of communication. So when you basically join this, I will add you to the repository, and you would have access to this. You don't have to be contributor to the repository. You can just have read-only access, as most of the people are in that scenario. And George and one of our colleagues and I are maintaining the repository at the moment. Then what we do is that you would know exactly what would be your connection information, your username and password, and that's basically your gateway to the system. Now, at the moment, we are controlling the access by firewall IP address. So either we have already added the VPN IP range from your university, or we need to do it. Either way, you would need to use that kind of VPN from universities, and we are opening access to the university IP addresses or VPN from the university IP address. So either is a on-premise landline of the university or VPN. There are cases that we open private IP addresses, but we try not to do that because there are a limited number of security rules that we can define. And the idea would be, once you get your IP in the system and you've got your user password, you have access to this database. And you will also have access to the Slack channel that you talk to us if something goes wrong, and preferably let everyone know if you're running BigQuery, because that affects everyone else who are using those machines. Okay, so that is technically kind of end of my presentation. So we have 6 minutes to talk about this.
We could talk about this till cows come home, the proverbially speaking. But it is it's very interesting. I mean, very well presented and very interesting topic as well. And so, do we have any questions? Because I don't want to take the privilege of chairing this to get precedence. So I thought I saw someone waving, and okay. So of course, like everyone else, I'm also jumping at the possibility of getting access, but I'm not trying to do it online right now. But but I do have. So when you actually created this Australian research data infrastructure, is it so? It looks like it is not just a simple filter, right? It is not just a filter on the global database, and so it looks like you have taken the data out, replicated it, and obviously with the live links and so on, and then you are furnishing it in-house. Is that correct?
That is correct. Also worth mentioning that the reason that we got to this is that when probably most people here have heard or seen the MoreBrain report on a value of persistent identifier. That is how we got to this project. When Josh Brown from MoreBrain asked us a couple of questions, we thought, okay, that's easy to answer, but then ask more questions and things got more complicated. And we said, okay, we're going to filter everything, create a small graph database for MoreBrain, and they can do whatever they want. Obviously, as you mentioned, is not a simple filter. Once we start filtering, we realize, oh, that's get quite messy. So we have to build these rules of optimization and clearing. And something we initially thought it's going to take like a just weekend job. It took about a month and a half to happen. Then we said, okay, now that it works, let's just share it with others. So that was the kind of motivation behind it. We initially didn't intend to do this. It just happened because of the specific demand. But now there is a very functional code here to produce this. I believe this can be a valuable source for a lot of clever people who do amazing things with graphs. And I've seen from the bibliometry community and social network analysis community that having access to graph like this is quite a powerful platform for running their own research. So even people who have no interest in Australian research, given that it is a real life-size graph, it provides a very good playground for their own computer science research. But for some of us who have interest in research and research impact, obviously this is a much more valuable platform.
Absolutely, absolutely. So I'm waiting if there are any other questions before I fire my next question. So maybe I will ask. I can't contain myself anymore. So when you actually have this, you have replicated an infrastructure or the whole system for Australian research. What are the challenges that you faced? And secondly, how replicable it is for any other type of, let me call it filter. Maybe let's say New Zealand, or maybe filter based on something else.
Oh, for different countries, it is very replicable. In fact, we started to already talk to other countries about doing something similar for different flavor of the same technology. So it's replicable easily for different countries. But if you want to replicate this for other things, like for example, you say, I want to create a graph of research related to the renewable energy or research related to the AI. We have another engine for that. There's a knowledge mining engine that does that sort of things. It gets far more complicated than this, because in the country type filter, it's very easy. You know, things that start from a country, obviously things that's country code, and you can go from there. But other type of filterings are more complicated. So in this case, it is replicable for different countries easily. The challenge is, well, there are two challenges here. One is that one challenge which you already manage is that finding the right way to optimize this, which is already addressed that. And the second one here is that those rules might change because the global pit graph continuously changing. So while we have done this now, but it requires continuous thinking and community to develop. So we are looking for active group of collaborators to work with us. This is one of those things that would only thrive if there is a good community around it.
Absolutely, absolutely. And yes, I think Ming Fang, do you have?
Yeah, just a question. And so in your graph, do you just store the pit and the relation, or do you store metadata as well?
No, full metadata. Some of them are complete. It's a research graph schema models. You can check the schema, but it has most of the useful things for papers, like the publication date, list of all the co-authors, where published, this sort of thing. So you get, it's not full detail. For example, for data sets, we don't hold the size of the data or access right or these sort of things, but it has a general metadata information. As you probably remember from the very early days of this project, it has very much RefCS type flavor. So that kind of is built on the same backbone.
Okay, cool.
Brilliant, brilliant. Thank you so much. We, as I said, we can keep talking till cows come home, but maybe that's something that we keep it to ourselves. And but thank you so much for the talk, Amir, as well as Alison, Ali, and Jeaneth. Thank you so much as well. And I also take this opportunity to thank everyone who has attended the session. And so we may have follow-ons. And also, we do have a survey going on in ML4AU. ML4AU is a community of practice. Such communities survive because of your participation. So we do want your participation and contribution. I don't mean monetarily, your time and your interest in the community. And So, Brent, do you have anything to say, or did I put you on the spot?
Well, yes, but as far as anything to say, no, I was just turning the camera on because it's discussion time and hangout time or whatever. And so like, okay, camera, go.
Yes.
But no, I don't have anything to say. I was just listening.
Absolutely. I'm happy to hang out here and continue chatting. And yes, so thank you. And then yeah, so we will have future talks, and may even have a repeat of some of these or an extension of some of these in the future. And so look out for the space. And so everyone who has either signed up on Slack channel or on the Excel sheet, you will receive the recordings as well as the updates about the future events. So with that, I thank you and conclude the session.
Thank you very much. Have a good day.
Thank you.
Thank you. Bye.
Yeah.
Bye.
I'll have meeting at 6:30 as
Oh,
well.
great.
Yeah, bye.
Bye. Okay then. See you.
Thanks, Nana.
Hi, Julia.
That was
Hope
Amir's.
it was useful.
Yeah, Amir's. Well, the other one I didn't focus on quite as much, but Amir's, I really appreciated. That was
Okay,
amazing.
One moment.
Sorry?
Give me 1 second.